All right, so in this video, I want to talk a little bit about how we're going to take these 5 wave variables and somehow relate them together numerically. I want an equation that'll say that, one of them is equal to, I don't know, I'm making this part up, something squared over something. I don't want to give it away yet. But I want to see if we can relate these things numerically together. And first of all, we're going to start by pointing out that amplitude won't show up in there. We saw this on the activity where you played with the stimulation of the wave on a string, that amplitude, or the height of the wave, doesn't relate to the rest of these things. Velocity is how fast it moves to the side. Frequency is whether you have a lot of waves very often or just a few. Wavelength is, of course, whether the waves are long or whether they're short, and the amplitude doesn't affect any of those. I'm also not going to include period on here because frequency and period are just two ways of describing the exact same thing. And so I'm just not going to use it. Period doesn't seem to matter so much. We don't really care. So really what we're going to wind up with is some equation that relates with velocity, frequency, and wavelength and how they go together. And I guess I wouldn't have a third thing on here, right? So I don't know what the equation is going to look like yet. In order for us to figure out what this equation is going to look like, we're going to go back to the first unit of this class and talk about the units. Right, so the units of velocity, the units of frequency, and the units of wavelength, and we're going to set up basically a unit conversion process here that will allow us to see how these things are related to each other. And as a reminder here, the velocity is controlled by the medium that the waves are traveling through, and the frequency is controlled by you. So you get to control how often you're wiggling something up and down, and the medium controls the speed that those wiggles travel through it, which means the wavelength is the dependent variable in the situation because it depends, so that's kind of clever why they call it that, on the velocity and the frequency. And so what I want to do is have an equation for wavelength based on the other two. So it might say something like wavelength is velocity times frequency, or maybe it's velocity divided by frequency, maybe it's frequency over velocity, maybe it's 1 over both of them, maybe it's the integral of frequency squared times the tangent of velocity df from 0 to pi over 2. Yeah, probably not that one. You guys don't know integral calculus yet, so no, it's not going to be that one. But it's probably going to be one of these forms right here, and we're going to use unit conversion to figure it out. And so the way I'm going to set this up is I need to figure out what am I going to multiply together to leave me with units of meters per wave. And so I'm going to go back up to my units of the other two and see what I can work with here. And I see on top is meters, and oh look, here's meters per second right there. So I'll start by putting velocity as one of my first terms, meters per, and just to stay with my color code here, I'm going to go back to the navy blue for seconds. So I need to multiply meters per second by something to wind up with meters per wave. I'm not changing the top, I'm just changing the bottom. So I'm either going to be multiplying this by seconds over wave or by wave over seconds, right? Because really what I need to do is convert seconds into waves right there. So I have right now seconds is already on the bottom. In order for me to get rid of it, I need seconds to show up on the top. So that's not this form, that's going to be that form right there. So if I go through, I'm going to erase that highlighted mark real quick. If I go through and say, well, fine, I need to multiply by meters per second times seconds, come on green, seconds per wave. And when I do that, what I will see is that the seconds cancel out and it leaves me with meters per wave. Well, meters per second is velocity. That is the units of that form of that variable right there. Let's go back up and take a look at what seconds per wave are. And it sure looks a whole lot like frequency, but it's upside down, isn't it? Frequency is waves per second. What I need to multiply this thing by is seconds per wave. And so what this is the upside down frequency, or the inverse, the reciprocal, if you will, of frequency. So mathematically what we could say then is it's going to, wavelength is the same thing as, or shall be equal to, velocity times the upside down frequency, which is this exact same thing as saying 1 over frequency. Now, a number times 1 over, I don't know what that is, times 1 over something is the same thing as dividing it. So what we're going to wind up with is velocity divided by frequency is the same thing as wavelength. This, ladies and gentlemen, boys and girls, is the wave equation. And as a reminder here, the velocity is controlled by the medium, so it gets to choose how fast the waves are allowed to travel through it. Frequency is controlled by you. You get to control how fast you shake the slinky up and down, or how fast, or how often rather, you splash in the swimming pool or whatever. And I think of this over here as like the result. Right? That's the effect, really. If you think of this side as like being the cause, then this side over here is going to be the effect. So we can come down and do a quick example problem on here, and it says like this. Let's see, a student wiggles a slinky 4 times per second. Ooh, that's frequency. And the waves reach 2 meters long. Ooh, that's wavelength right there. How fast are they moving? So what's asking us for velocity. So I'm going to break out my wave equation, which, yep, frequency over velocity equals wavelength. I said that wrong. Velocity over frequency equals wavelength. And in this case, I'm going to have a wavelength of 2 is equal to my unknown velocity over a frequency of 4. In other words, what do I divide by 4 to get 2? And the answer, of course, winds up being 8 meters per second, right? 8's the only number that you can divide by 4 and have it be equal to 2 right there. So we solved this not just for lambda. We're able to solve for any of these. That's the nice thing about a 3-variable equation, is that you have the ability to solve for the third one if you know any of the other two. So let's try another one here. What frequency does a set of 3 meter long, okay, so that's wavelength, have if they move across the water at 15 meters per second? Okay, that's velocity. So we're being asked for frequency right there. Wavelength is V over F. And it looks like my wavelength is going to be 3 meters. Velocity is 15 meters per second. Oops, that should be an F for frequency, or frequency. All right, so 15 divided by what is 3? Well, 15 is 5 times bigger than 3. That means this waves must have a frequency of 5 hertz. That's it. All right, so the last concept builder that we're going to do in mechanical waves is kind of putting everything together. It's going to be asking you to relate wave anatomy. It's going to be asking you to relate the wave equation. It's going to be asking you to see how all the different parts of a mechanical wave fit together. And it's going to look, oh good, these things decided to resize themselves just for fun. That's great. Unfortunately, I have right now, because if I stop and resize this, are you kidding me right now? Wow, there we go. If I start the video all over again, I can't just like pick it back up. I have to do it all in one take. Anyway, so while I'm doing that, you guys think of something funny, right? Tell yourself a joke, crack yourself up. All right, so this is an example of one of the problems that you'll see on our very last concept builder, and it's a 2-step problem. What they're going to do first is ask you to physically show where the other boat ought to be here that is described in the situation. And once you get that right, then it's going to ask you some of the questions that will force you to use the wave equation and the definitions of the different wave variables. So reading this thing, 2 boats are anchored in the harbor, separated by a horizontal distance of 20. Okay. They bob up and down. When one boat is at its highest point, so that's right here, the other is at its lowest point, and there are 2 wave crests between them. So I'm going to be saying, is it here, is it here, is it here, is it here, or is it here? It's in one of those spots right there. It's got to be at its lowest point. And when you toggle through, oops, sorry, undo that. When you tap this diagram, you'll see you can position that second boat wherever you want. Well, it says that it's at its, the other is at its lowest point. What is going on here? The other is at its, stop that, lowest point, and there are 2 wave crests in between them. So 1, 2, that means this guy must be in this spot right there. And I hit check diagram, and sure enough, that away, you're good. So now it's going to ask me to go through and identify or calculate the values for all 5 of the wave variables. And so we're going to go through, let's do this first. I'm going to draw me my equilibrium position. That's kind of crummy right there. Let's move that up just a bit. Great. And I like to go through and kind of label them off. So like here's 1 wave, there's 2 waves, there's 3 waves, there's 4. Interesting. Actually, let's do that a different way. Let's count crests. So there's 1 full wave, 2 full waves, 3 full waves. So that's 1, 2, 3 full waves. and it says that they're separated by a horizontal distance of 20. So this right here is wrong. This right here is 20 meters, but that is 1, 2, and a half. So 20 meters is 2.5 waves, which means the wavelength of this thing is going to be 8 meters. If 2.5 of them are 20 meters long, one wavelength is from there to there, or from there to there, or from there to there. So I just divide 20 by 2.5. Next up, it makes exactly 4 complete up and down cycles every 12 seconds. So that's relating to frequency. So that's saying the frequency is 4 waves every 12 seconds. That reduces down to 1/3 hertz. And it says to include at least 2 significant digits. So you can't put fractions in there. You're going to have to put decimals. Significant digits, how many decimal places? So I'm going to just say 0.333. Oops, that's not supposed to be seconds, is it? That's supposed to be hertz. You didn't need to have a third decimal place. I like to because I'm just fancy like that. So 0.333. And you don't actually need to have the units in there. They're just looking for the numbers. Period is the opposite of frequency. Period is not going to be waves per second. It's going to be seconds per wave. So all I need to do is flip this upside down, and instead of 4 over 12, I would get 12 over 4, because it's how many seconds each wave takes. Well, 12 seconds on 4 waves means this thing has a period of 3 seconds. Okay, amplitude. Let me clean my drawing up a little bit here so we can see a little bit better. Amplitude is this value right here. How high did you stretch above the equilibrium position? And it says the vertical distance between the boat's highest and lowest position is 2.6. So that's telling me that this right here, this height, from all the way down the crest, all the way up here to the trough is 2.6. And if that's 2.6, this has to be half of it, right? So if this distance is 2.6, this has to be half, or 1.3. So that's got an amplitude, go back to purple, because of 1.3 meters. Last but not least, the speed. Well, our wave equation says lambda is velocity over frequency. And I know that my wavelength is 8, and my frequency is 1/3, so 0.33333. Hopefully we've had enough algebra right now to know that dividing by a fraction, you just flip and multiply. So what I could do is say 8 equals velocity times 3. Divided by 1/3 is the same thing as timesing by 3. And then I wind up solving this thing to get 8 over 3, which is 2.666666. This is going on forever. 2.666. So that's it, folks. Ladies and gentlemen, that is it. That is what I'm going to ask you all to do here, is to prove what you've learned so far about waves, to analyze the situation in pictures and in some simple numbers right here. And this is what we're going to be doing together in your breakout rooms on Thursday. You'll get a chance to kind of help each other out and work on this together.